Prepare yourselves for an inestimable upheaval of phenomenal extents. Betelgeuse, the red Goliath star, balanced on the edge of our cosmic system, is conveying unfavorable messages through the universe. Utilizing the James Webb Space Telescope, cosmologists have revealed something significantly agitating about this gigantic divine body. As eminent astrophysicist Brian Cox gives a grave warning, the inquiry looms. Are we on the cliff of witnessing a horrendous cosmic explosion blast that could forever change the night sky as we know it? In the grand tapestry of the universe, where stars are born, live, and die in dramatic fashion, one star has recently captured the imagination and concern of astronomers and the public alike. This star is Betelgeuse, a red supergiant of colossal proportions and age, prominently situated in the constellation Orion. Its distinctive reddish hue and variable brightness have long been a source of fascination, but recent developments have intensified interest in this celestial giant. We are now on the cusp of a potentially monumental event in the life cycle of this star. But what could these changes in Betelgeuse imply? Are we witnessing the prelude to a cosmic spectacle of unimaginable scale? Betelgeuse, over 1,000 times larger than our Sun, is a stellar behemoth. Its epic size is nearly beyond human comprehension. Imagine a star so vast that, were it to replace our Sun, its surface would extend beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars in its celestial embrace. This incredible size is not just a testament to Betelgeuse's physical attributes, but also reflects its stage in the stellar life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, a phase marked by expansion and cooling after a life spent fusing hydrogen into helium in its core. But what about the age of Betelgeuse? This star, believed to be around 8.5 million years old, is relatively young in human terms, but ancient in the context of stellar lifetimes. Its current red supergiant phase marks the end of millions of years of stellar evolution, a time characterized by dramatic changes and processes that have transformed it from a hot blue star into the red giant we see today. The life cycle of stars like Betelgeuse is a story of transformation, driven by the relentless forces of nuclear fusion and gravity. Betelgeuse's characteristic reddish hue is another sign of its current stage. The red color results from its relatively cooler surface temperature compared to other stars like our Sun. While the Sun's surface temperature is around 5,500 Kelvin, Betelgeuse's cooler surface registers temperatures of around 3,500 Kelvin. This cooler temperature allows Betelgeuse to emit light at wavelengths that give it a reddish appearance. However, this color is not just a visual trait. It provides clues about the star's physical state and the processes happening within its vast gaseous span. Adding to Betelgeuse's mystique is its historical color change. Ancient Roman and Chinese writings suggest that around 2,000 years ago, Betelgeuse was yellow. It was only in the 9th century that Arabic scholars first described it as red. This color shift over human history is not just a footnote in the annals of astronomy, but a clue to the star's evolutionary path. The variable brightness of Betelgeuse is another intriguing aspect. It is a semi-regular variable star, which means its light periodically waxes and wanes. This variability is a characteristic dance of radiance that has captivated astronomers and sky watchers for centuries. Typically, Betelgeuse goes through a 400-day cycle, along with a longer cycle that spans around 5 years. These cycles have been documented as far back as 1836 by Sir John Herschel, and possibly even earlier in indigenous oral traditions. However, what makes Betelgeuse truly enigmatic is not just its changing brightness, but its anomalies. Unlike many stars that follow a predictable pattern, Betelgeuse occasionally deviates from its rhythmic dimming and brightening, hinting at complex and less understood processes occurring within its massive form. A recent remarkable discovery about Betelgeuse captured the attention of astronomers worldwide with an unexpected and dramatic change in its appearance, an event now widely known as the Great Dimming. In late 2019, the red supergiant Betelgeuse, one of the brightest stars in the night sky and a prominent feature of the Orion constellation, began to dim mysteriously. The star's dimming was so pronounced that it began losing its glow at an average rate of 0.01 magnitudes per day, reaching its lowest brightness in February 2020. Betelgeuse, normally visible to the naked eye even in light-polluted areas, became noticeably fainter, a change even visible to amateur observers. However, there's one issue with trying to monitor Betelgeuse's activities: the time paradox. When we look at a star like Betelgeuse, we are not seeing it as it exists in the present but as it was in the past, due to the time it takes for light to travel to us. In Betelgeuse's case, at approximately 725 light-years away, the light we see today left the star nearly 7 centuries ago. This delay makes it challenging to predict and monitor sudden changes in a star's behavior, as we are essentially looking into its past. The Great Dimming Event served as a reminder of the inherent difficulties in real-time astronomical observations and the limitations of our understanding when dealing with the vast cosmic scales and time paradoxes they present. The unfolding of Betelgeuse's stellar drama was closely monitored by Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team. They used Hubble to observe the behemoth star as part of a 3-year study to track variations in Betelgeuse's outer atmosphere. These observations offered remarkable insights into the dynamics of a variable star like Betelgeuse, which routinely expands and contracts, causing fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed the researchers to probe the layers above the star's surface, which were partially heated by the star's turbulent convection cells. Further analysis of the Hubble spectra, taken at different points throughout 2019 and 2020, helped measure the movement of material in Betelgeuse's outer atmosphere. Specifically, the spectra focused on magnesium-2 lines, which are indicative of the star's atmospheric conditions. These observations showed material moving at speeds of around 200,000 miles per hour from the star's surface into its outer atmosphere. This hot, dense material eventually extended millions of miles from Betelgeuse and was the precursor to the dust cloud that led to the star's dimming. Dupree and her team estimated that about twice the normal amount of material from Betelgeuse's southern hemisphere was lost over the 3 months of the outburst. This mass loss was significant, especially considering that Betelgeuse, like all stars, stars consistently lose mass, though at a rate far more noteworthy than that of our Sun. The size of this mass discharge and the ensuing dimming flash sparked conversations among astronomers about whether this event could be a precursor to a cosmic explosion. The vicinity of Betelgeuse, around 725 light-years from Earth, adds to the interest, as any such explosion would be visible from Earth, providing an intriguing opportunity to observe a supernova up close. Yet the question remains, what does this dimming event predict for Betelgeuse's future? Is it a sign of an impending supernova or simply an interesting episode in the star's long and complex life? Several theories were proposed to explain this abrupt transformation. One pervasive hypothesis suggested a slowdown in the supernova process, a theory that gained momentum due to the common belief that Betelgeuse is nearing the end of its life. Another popular hypothesis implicated dust, potentially from the star itself, clouding our view. Betelgeuse, like other red supergiants, is known to shed material, and it was thought this material could form a dust cloud thick enough to dim the star's light from our perspective. A third explanation considered changes in the star's photosphere, the visible surface layer, which could affect its brightness. Spectroscopic studies indicated a drop in Betelgeuse's effective temperature, suggesting the dimming could be due to a large dark spot on the star's surface. This theory was supported by observations that Betelgeuse's temperature fell by about 170 Kelvin around the time of the dimming, pointing to significant changes on its surface. Ultimately, the key to understanding this strange phenomenon came from space. Through the Hubble Space Telescope, Hubble's observations revealed that the dimming of Betelgeuse was likely caused by a significant ejection of hot material into space. This material formed a dust cloud that obscured part of the star's surface, reducing the amount of light reaching us. The dust cloud was believed to have originated from very hot plasma, which erupted from a large convection cell on the star's surface and traveled through its atmosphere to the colder outer layers. As it cooled, it formed dust grains, creating a cloud that blocked light from about a quarter of the star's surface. Hubble's ultraviolet light spectroscopic observations, which began in January 2019, were crucial in piecing together the timeline leading up to Betelgeuse's dimming. These observations captured signs of dense heated material moving through the star's atmosphere months before the dimming in December 2019. Several ground-based telescopes also observed the star dimming, particularly in its southern hemisphere. The expelled material, believed to weigh several times as much as our moon, was a significant event, not just for Betelgeuse but for our understanding of stellar mechanics. But what does such a massive ejection of material mean for Betelgeuse and supernova theories at large? The implications are profound. Traditional understanding holds that red supergiants like Betelgeuse shed mass at a relatively steady rate before the explosive end of their lives. However, the size of this ejection challenges this idea, suggesting a more violent and possibly unpredictable end-of-life stage for these stars. Could Betelgeuse be preparing for its grand finale, a supernova, within the next few centuries? Recent studies speculate on the timing of such an event, suggesting it could happen sooner than previously thought, perhaps in just a few decades. As Betelgeuse tears through space at roughly 67,000 miles per hour, it creates a bow shock, much like the wake of a moving ship. This phenomenon provides fascinating evidence of the star's dynamic nature and its interaction with the surrounding cosmic environment. The study of this bow shock not only informs us about Betelgeuse's current state, but also contributes to our understanding of stellar evolution and mass loss processes. But what about Betelgeuse's recent behavior? Its surface has been observed to cool and become less dense following the ejection event, leaving the star in an unstable state even years later. Hydrodynamic simulations suggest a connection between the star's convective activities, the mass ejection, and its subsequent pulsation mode. This ongoing instability raises questions about the internal processes driving these changes and how they might culminate in the future. Betelgeuse's mass loss rate, as observed, is significantly higher than many other stars, indicating a complex interplay of internal forces. The pulsation, partly responsible for this mass loss, is limited by the steady energy dissipation through shock heating and mass ejection. These observations highlight the dynamic and somewhat unpredictable nature of Betelgeuse's life cycle, prompting astronomers to reconsider their models of stellar evolution. But with all these dramatic changes, one might wonder, is Betelgeuse on the verge of going supernova? The question looms large in the astronomical community. While the timing of such an event remains uncertain, the recent massive mass ejection has undoubtedly shifted the discussion, hinting at a more imminent end than previously expected. As the astronomical community eagerly watches Betelgeuse, another cosmic event captures attention and offers a striking comparative study: the supernova SN 2023 ISF. This spectacular explosion occurred in the galaxy Messier 101, the Pinwheel Galaxy, located a mere 21 million light-years away. Discovered in May 2023, SN 2023 ISF isn't just another supernova. It's the closest one observed in recent years, offering an invaluable close-up of a star's catastrophic finale. The discovery of SN 2023 ISF was nothing short of a cosmic coup. Koichi Itagaki, a renowned amateur astronomer, first spotted the rapidly brightening spot on the outskirts of Messier 101 using a modest 0.35 m telescope. Once announced, the astronomical community sprang into action, with telescopes worldwide both on Earth and in space, turning to capture the unfolding drama of this newborn supernova. The subsequent race to monitor SN 2023 ISF's light curve provided critical insights into the nature of the explosion and the environment surrounding the doomed star. Spectral analysis revealed a wealth of bright emission lines, a testament to the violent interaction between the expanding supernova shockwave and the gas surrounding the star. What makes SN 2023 ISF particularly fascinating is the dense shell of gas that developed, significantly affecting the breakout of the shockwave from the star's core. A solid, consistent breeze had been shedding material from the star before the blast, or the star experienced an irregular explosion, flinging material into space. Regardless, it's assessed that the star lost up to a solar mass of material in the last 1 to 2 years of its life, demonstrating that its final moments were anything but peaceful. Identifying the forebear of SN 2023 ISF has become a focal point of study through various methods and datasets. Scientists have converged on a likely candidate, a red supergiant. By studying the details of SN 2023 ISF's explosion, including its progenitor's characteristics and the mechanisms leading up to its final explosion, astronomers can refine their models of stellar evolution and supernova mechanics. These insights directly inform our understanding of Betelgeuse's current state and its potential path to a supernova, offering a clearer picture of what signs to look for and how to interpret the massive red giant's complex behaviors. But when will Betelgeuse explode into a supernova? Research from Japan's Tohoku University has proposed that Betelgeuse may currently be in the carbon-burning stage of its life, a stage that typically precedes the end of a star's life. The head of this study, Heiso, suggests that the star's core could collapse a few tens of years after the carbon is depleted. On the other hand, researchers from Hungary's Konkoly Observatory believe Betelgeuse is in an earlier helium-burning stage. Despite these differing views, there is consensus that Betelgeuse is likely to be the next supernova in the Milky Way, although this event might not happen for another 100,000 years. Historical observations of supernovae have provided valuable insights into stellar deaths. The earliest confirmed record of a supernova, dating back to 185 CE, was observed as a bright star that took around 8 months to fade from the sky. Since then, several significant supernovae have been recorded, including SN 1604, the brightest recorded star ever to appear in our night sky, visible across multiple parts of the world, and SN 1054, which resulted in the formation of the Crab Nebula and was visible in daylight for 23 days. The most recent supernova seen in the Milky Way was SN 1987A in the Large Magellanic Cloud, observed within hours of its light reaching Earth. This marked the first supernova detected through neutrino emission and was observed across every band of the electromagnetic spectrum. These observations have been crucial in developing successful models of supernova behavior and understanding their role in star formation. So, what if the night sky suddenly burst into a brilliant display of cosmic fireworks, captivating our gaze with the bright explosion of a star? Imagine for a moment the once familiar constellation of Orion adorned with a new blazing gem, Betelgeuse, one of its prominent stars, transformed into a bright supernova. Could this awe-inspiring event affect Earth in any way? Betelgeuse's impending supernova is classified as a core collapse supernova, a type of explosion that occurs when massive stars exhaust their nuclear fuel and can no longer support their own gravitational collapse. Core collapse supernovae are among the most energetic and catastrophic events in the universe. When Betelgeuse eventually goes supernova, it will release as much energy in an instant as our Sun will emit over its entire lifespan of billions of years. The energy output from a supernova primarily manifests as electromagnetic radiation, including visible light, X-rays, and gamma rays. However, the most immediate and visible impact of a Betelgeuse supernova would be a spectacular light show in our night sky. The explosion would temporarily outshine the moon and would be visible even during the day. Imagine looking up at the daytime sky and seeing a second, incredibly bright sun appear for a few weeks or even months. The event would be a breathtaking celestial display, captivating astronomers and stargazers alike. But as captivating as the visual spectacle of a Betelgeuse supernova would be, its true significance lies in the scientific opportunities it presents. Supernovae, especially those of massive stars like Betelgeuse, are cosmic laboratories that offer valuable insights into the fundamental workings of the universe. One of the immediate benefits of observing a Betelgeuse supernova would be the opportunity to witness the final stages of stellar evolution up close. When massive stars like Betelgeuse explode, they distribute elements forged within their cores, including heavy elements like iron, into space. This process is responsible for enriching the universe with the building blocks of planets, stars, and life itself. By studying the spectroscopic signatures and the distribution of these elements in the aftermath of a supernova, scientists can gain a deeper understanding of how stars evolve, fuse elements, and contribute to the formation of new celestial bodies. This knowledge is crucial for unraveling the history and composition of the universe. While the visible light from a Betelgeuse supernova would be impressive, an equally fascinating part of the event is the emission of neutrinos, subatomic particles that are notoriously difficult to detect because they rarely interact with matter. However, in the extreme environment of a supernova, they are produced in vast quantities. These elusive neutrinos offer a unique window into the heart of a dying star. They can provide information about the core collapse process, shedding light on the fundamental forces and particles at work during a supernova explosion. Detecting and analyzing these neutrinos would be a groundbreaking scientific achievement, potentially unlocking secrets about the universe's most extreme conditions. The observation of a Betelgeuse supernova could also have implications for our understanding of the universe's expansion and the mysterious force known as dark energy. In the late 1990s, observations of distant supernovae led to the discovery that the expansion of the universe is accelerating, not slowing down as previously thought. Betelgeuse's supernova, being relatively close in cosmic terms, would provide an important data point for studying the expansion rate of the universe and the role of dark energy in driving it. It could help refine our understanding of these fundamental cosmological concepts, possibly revealing new mysteries about the fate and nature of the universe. But what could be the potential consequences of a Betelgeuse supernova on Earth? Is humanity at risk? Considering the vast distances that separate us, this is an unlikely possibility. To put the scale of our universe into perspective, consider that 1 light-year is roughly 5.88 trillion miles. Betelgeuse, at 725 light-years away, is more than 4,267 trillion miles distant from our planet. This immense separation provides a degree of cosmic insulation, and any direct physical harm to Earth from the explosion itself is highly unlikely.